Now let's talk about system calls. So based on what we've said, we understand that the operating system at some level operates like a library in the sense that it provides services, but it operates in a higher level of privilege and it can do things that normal libraries cannot do. So in other words, we understand these three lines of text that are written over here. The question is, why do we want to do this, or why this way of designing a system is desirable? There could be some obvious answers, and I'm going to mention some of them. The first obvious answer is security. By allowing operating system to have exclusive access to the machine and by limiting the ability of normal code to basically do nothing, we can make sure that the operating system can encapsulate every program or every user program inside an own box, such that a malicious program cannot do too much harm, or a buggy program cannot do too much damage. So for example, if the programs were writing their own data to the disk, a bug in a program could result in the files of some other program being unreadable. Whereas if you have a bug in your program that is writing a file, you might be damaging your own file, but you will not be overwriting somebody else's file. The operating system ensures that you can't do that. So protection from malicious code or buggy code is one big reason. The other big reason is that, of course, having common things being implemented once is desirable, such that the programs can focus on the things that they want to do rather than trying to reinvent the wheel. So those two kind of the main reasons we want to have these separations, and we would like to have system calls. Okay. So let's look at the details of how system calls operate. With system calls, we can jump to specific location in kernel space. What this means that it is essentially like a library call, except that you can only jump to specific locations. This is often supported by dedicated instructions depending on the platform. So syscall in an Intel machine and SWI is in ARM architecture. So these are the two instructions that you can use for system call. And the way these operations work is that typically the operating system, almost always the operating system sets up the way these instructions should work. Based on what we have discussed, the machine usually has a lot of system registers, and the systems that are exclusively can be used by the operating system. The operating system uses them to set up its code or these instructions in such a way that they jump to specific locations that the operating system has placed a code to handle these system calls. And we're going to look at the details of system calls later, so probably this will be more clear later on. But I have a picture here that corresponds to a 64-bit Intel machine. So in a 64-bit Intel machine, as we've discussed, there's 48 bits of virtual memory. So that means that these high 4 numbers in hex, which corresponds to 16 numbers, don't matter. And what matters is this lower 48. Okay, inside this lower 48, these lower 48 divided into two parts: the canonical lower half and the canonical upper half. The difference between them is that canonical lower half have 0 for the bit number 48 or bit number 47 if you count from 0, whereas these addresses have a 1. By design, for example, Linux will sit in the upper half, whereas normal programs will sit in the lower half. Remember, this is just the virtual memory, right? So there is nothing as far as I know with respect to physical location, but the virtual address is cut in half in this way. And with a system call, you can jump to a memory location in the higher half. Let's look at the documentations of these instructions. So if you look up the documentation of, say, SWI instruction, you'll see that it explains essentially how it is done. And in particular, what it will also specify is that this instruction escalates or increases the exception level in the sense that it increases the privilege. In other words, once you use it as a user from a normal user privilege, once you make the jump to the kernel space, your privilege has been elevated to the privilege of the operating system. So this instruction elevates the amount of privilege you have, and the same is happening for the syscall in an Intel machine. So here, this is from Intel documents. Remember that in Intel, privilege level 0 means highest level of privilege. So essentially it will increase or decrease the privilege in this case to 0, and will also jump to a location specified by this register. So this whole thing is a name of one register, and this register can only be written by the operating system, and it has the address of where you want to go. Okay, and so this is how you make a jump to the specific location in the kernel space, and your privilege is also increased. Just to show you the opposite instruction, systhread in Intel machine is an instruction that returns from a syscall. It kind of essentially undoes the steps of syscall. It lowers the privilege level and all that stuff. Okay. So this is how system calls work. Let's look at some of the details here. So every operating system will obviously have different conventions when it comes to system calls. So note that the hardware only provides the hardware support for system calls. It doesn't really specify how system calls should be used. And there is big difference between, say, how Windows will do it, how Linux will do it, or even how 32-bit Linux versus 64-bit Linux will do it. In Linux, you can read about system calls using two manuals pages. I'm going to show them quickly on the screen. So if you run man syscall, so this is a manual page that specifies how parameters are passed. So if you look up, so this is a 32-bit ARM. You would put the syscall number, which is R7. In an Intel machine, you would put the syscall number in RAX. And then if you scroll further down, you will see that it mentions how the parameters are passed. So in an Intel, 64-bit Intel, you would pass normally, like first parameter RDI, second parameter RSI, and so on. And same for the ARM architecture. So this manual pages will tell you how to pass parameters to Linux kernel whenever you're calling a system call. The next manual page that is useful is syscalls. It has the list of all system calls by Linux. Let's look at one of them. So write. So this number 2 means that you need to look up the second page of the manual. So for the system call write, so what we call is a man to write 2 here is the second page of the manual, second chapter, I guess. So Linux kernel is written in C, so there are C wrappers for calling system calls. So this is essentially a wrapper that will call the system call. It would plug in the correct number for the system call of write, but we'll see the documentation here that the write system call has 3 parameters. So one integer value that describes which file you're trying to write to. This is a string you're trying to write to, and this is how many bytes you're trying to write to the file. So you need 3 parameters. And so this is what we're going to call. If you want to call it from C, this is basically how we would use it. If you want to call it from the assembly, you need to put the number of the system called in the register RAX. You could look this up in various headers or look it up online, but at some point you can look it up and you will realize that the system call write has number 1, so you put 1 into the register RAX. And then the rest of the parameters is passed normally. So the first parameter is which file we want to write. Again, if you recall, in Linux, there are by default 3 files are open for programs. So standard input, the standard output, and the standard error. And 1 is for the standard output, which is normal output to the terminal. So that's why we move 1 to the register RDI. Then the second parameter is what we want to write. We want to write this hello world message. So we put the starting address of this hello world. And finally, we put how many bytes we want to write. And in this case, in this assembly, we calculate how many bytes, not by counting how many bytes in the string hello world one by one by hand, by just doing a smart, by being a little bit smart here. Okay, so wait, over here. So basically, we are subtracting this address from this address, which should give us the number of bytes inside this hello world. Okay, and then we call the system call, and then it works. Just to show you the code on the screen, we can also see it. I have it here. So this is hello.s, exact same program, and then we can compile it with the assembler hello.o, and then we link hello.o to hello, and then we can run it. One interesting thing about Linux is that there is a program called strace, or command called strace, that you can run any program through it. So now I'm running my program hello through strace, and it would show me the system calls done by this program. So I will see that there is 3 system calls. The first one is for executing the program itself, and then the 2 other ones that we know exist in the program. The first one is for the write, and the other one for the exit. So the output might look a bit funny because the output of the hello program as well as the strace program are essentially placed on top of each other. strace prints to the standard error. So if I want to only have the standard error, I can redirect the standard output to say this garbage file, and this will filter out the standard output, which is where I'm writing in the hello program, and I only see the strace output. If I filter, whoops, what am I doing here? I should have done it this way, but it's the same thing. But if I filter out a standard error, I would only see the output of the hello, right? So this way you can see the strace output, and you can run any program through strace to see which system calls it uses, and also the parameters passed to the system call here. Okay, I think in the upcoming videos I'm going to show you more examples of the system calls, but that concludes essentially the basic understanding of system calls and what they are.